Right. Thank you, Tani, for the introduction. So hello, everyone. This is Wei Chen. I'm a physical oceanographer from NOAA Pacific Marine Environmental Lab. I just recently joined this PO Community of Practice co-lead team. So the goal of these IRPIC forums is to promote information exchange and discussion and collaborations, if possible, among its participants. So today, it's my pleasure to introduce our two speakers, Dylan Oldenburg, who is affiliated with NCAR, and Tom Haine, who is a professor from Johns Hopkins University. So just a quick format reminder, each speaker has about 15 minutes to speak, 15 to 20 minutes to speak, including quick Q&As to their presentation. And after both speakers are done, then we have the whole group Q&A and then discussion. So from at this moment, Dylan, the floor is yours. Thanks very much.
Great, thank you. Just one moment. Okay. Okay, and then great. Can you see the slides? Excellent. Okay, so so I currently work at NCAR, but actually this is work I did when I was a postdoc at Hui, working with Young-Oh Kwon, and Claude Franquignon, and then also some people at NCAR, so Steve Yeager and Go Khan and Hu Kim. And so I'm going to be talking about the role of ocean heat transport versus surface heat fluxes in driving Arctic warming and sea ice decline. And so there's increasing evidence that Arctic ocean warming is closely linked to increased ocean heat transport into the Arctic. So in particular, enhanced ocean heat transport through the Barents Sea opening has been found to explain most of the recent Barents Sea warming and sea ice loss, which are expected to intensify based on model predictions. On the Pacific side, ocean heat transport through the Bering Strait has also increased substantially recently, driving rapid warming and sea ice decline in the Chukchi Sea. So previous studies have analyzed the Arctic Ocean heat budget and how it changes over time in a range of CMET models. However, it's not clear how much additional heat accumulated in the Arctic Ocean is used to melt sea ice and how much is released to the atmosphere. It's also not clear which is the main heat source for the Arctic sea ice. Is it the ocean or the atmosphere which drives most of the sea ice warming or melting? So in this work, we focus on analyzing the Arctic Ocean heat budget and the CESN2 large ensemble under historical and future forcing, and then we further explore these last 2 points here. And so the large ensemble is a 100-member ensemble with different micro and macro perturbations and branch from different years of a pre-industrial control simulation. And so first I'll give you a brief outline of the presentation. So in part one, we study how the Arctic Ocean heat budget changes over time under anthropogenic forcing. So this includes historical and future predicted forcing. The goal here is to understand what drives the Arctic Ocean warming. So we want to determine the role that the ocean heat transport into the Arctic plays, as well as how this OHT, ocean heat transport, is partitioned between the different Arctic gateways. Heat can be transported through the different gateways that connect the Arctic to the southern regions. Where warming occurs can be dependent on where the heat is transported from. So surface heat fluxes also impact the heat budget. So you have ocean heat gain and loss from the ice and the atmosphere. And so finally, there is heat gain due to the fragile ice formation within the top ocean layer. So in autumn and winter, when ocean transfers heat to atmosphere and ice, the top ocean layer cools enough to freeze, and then ice crystals form within the layer, eventually forming part of the sea ice. And this ice formation process warms the ocean layer. We want to understand how much heat is lost to the ice versus the atmosphere. There's a question of how much of this additional heat in the ocean is used to melt the sea ice and how much is instead released to the atmosphere. And we're interested in what drives the sea ice loss, and sea ice is exposed to both the atmosphere and the ocean, of course. And so the question is, are heat fluxes from the atmosphere or from the ocean more important in driving sea ice warming and melting? So looking at it from the ice's perspective is also important. And so for the Arctic ocean heat budget, there are three terms that contribute to the heat budget. There's the lateral ocean heat transport through the various Arctic gateways. So this is computed for the sectors which we consider to be the southern bounds of the Arctic Ocean. So the Fram Strait, the Barents Sea opening, or the BSO, the Nares Strait, the Bering Strait, and the Barrow Strait. We do this rather than simply calculating the zonally integrated ocean heat transport across a particular latitude, because this method is based on actual physical pathways into the Arctic. It also allows us to study the ocean heat transport across the different sectors separately. And since these form a closed domain around the Arctic, they allow us to do heat budgets. And there are a few components of the ocean heat transport, which we calculate using monthly mean model output. This is the total ocean heat transport, which we can take directly from the model output. And the bar here refers to the monthly mean. So this is the monthly mean of the velocity times the temperature, computed on the fly as the model is running. So at a very high time resolution. This is the Eulerian mean ocean heat transport, calculated using monthly output velocity and temperature. And so this accounts for most of the ocean heat transport, but is missing variability at short time scales. So time scales shorter than monthly. And so hence we can compute the sub-monthly ocean heat transport as the residual between the total and the Eulerian mean ocean heat transport. It's important to note that these components do not include the parameterized bolus eddies or diffusion. And so the combined bolus and diffusion term can be approximated as the residual between the ocean heat content change and the rest of the heat budget terms we talked about. So in addition to the lateral ocean heat transport, we must also include sea surface heat fluxes, which we can take directly from model output as well. We include sensible and latent heat fluxes, long wave and short wave radiation fluxes, ice melt fluxes, snow, and runoff. And we must also include the fragile ice formation term. So the heat gained by the ocean due to the fragile ice formation within the ocean layer, which we discussed earlier. And this is calculated separately within the ocean model. And then for all of these quantities, we take annual means because we're interested in annual and longer time scale changes rather than seasonal variations. And so this shows the ensemble mean heat budget terms, where the ensemble mean refers to an average across all ensemble members. The shading indicates one standard deviation across the ensemble members. Positive values here indicate heat gain by the Arctic Ocean, and negative indicates heat loss by the Arctic Ocean. So here we can see that the ocean heat transport adds an additional 0.04 petawatts of heat to the Arctic over the course of the simulations. And this increase in the ocean heat transport starts at around 1975. Meanwhile, the sea surface heat fluxes remove an additional 0.02 petawatts of heat from the ocean over the course of the simulations. So hence about 50%, so half of the additional heat carried by the ocean heat transport is then removed via the surface, and the other half remains in the ocean. And this enhanced surface heat loss, however, is overwhelmed by the large increase in the ocean heat transport. And so as a result, the ocean heat content starts increasing at around 1990. And the rate of change of this ocean heat content reaches about 0.02 petawatts by the end of the simulations. And this total ocean heat content change over the simulations causes the Arctic Ocean to warm from 0.3 degrees on average to 0.46 degrees Celsius. This shows the ocean heat transport split into the different components. So we have the Eulerian mean, the sub-monthly eddy ocean heat transport, and the bolus and diffusion, estimated as the residual flux, as well as the fragile ice formation and the sea surface heat flux. So the ocean heat transport increase is largely driven by an increase in the Eulerian mean ocean heat transport. And the sub-monthly eddy and the residual flux also contribute substantially, so accounting for about 25%. And the sea surface heat loss increases over time, but not enough to compensate for the increased heat gain from the ocean heat transport. And fragile heat flux decreases over time as the ice formation declines. So the question is, which Arctic gateways experience the largest increases in the ocean heat transport? So the BSO OHT increases substantially, contributing about 50%, about half of the ocean heat transport increase. And the Fram Strait ocean heat transport first decreases and then eventually increases by about 0.01 petawatts, so accounting for about 25% of the increase in the ocean heat transport. And the Bering initially contributes very little during the 20th century, but eventually also increases to about 0.01 petawatts by 2100. The Nares Strait ocean heat transport and the Barrow Strait ocean heat transport also actually decrease over time and do not contribute to the increased ocean heat transport. So one question one may ask is whether these changes are driven by changes in volume fluxes across the sectors. So this shows the net volume flux through the same volume transport through the same Arctic gateways. Enhanced Fram Strait OHT can be explained partially by an increase in the magnitude of the volume transport towards the end of the simulations, but this is not the case for the BSO and the Bering Strait. Hence, volume flux changes cannot explain most of the OHT increase. And interestingly, there seems to be a link between the volume flux through the Fram Strait and the Nares Straits. The changes more or less compensate each other towards the end of the simulations. So the next question is, how much of the different types of sea surface heat fluxes contribute to the Arctic Ocean heat changes? So we have the shortwave and the long wave radiation fluxes, as well as the sensible and latent heat fluxes, and snow ice melt and runoff. We want to understand how much heat is lost to the ice versus the atmosphere, as we said before. So this shows the annual mean sea surface heat fluxes over time. So the question is, which components are most important in driving the sea surface heat loss that we see? And so we can see that absorbed shortwave increases dramatically as the surface albedo decreases as the sea ice declines. Concurrently, the long wave radiation becomes more negative over time, likely due to increased Arctic Ocean temperature and increased exposure to the atmosphere. And though incoming long wave radiation also increases, the increased outgoing long wave radiation dominates. And the latent heat flux also increases due to increased evaporation as a result of warmer water, as well as the increased exposure to the atmosphere. The sensible heat fluxes also increase, and the sea ice melt component decreases over time as the sea ice starts to decline. And then there's also heat loss due to snow melt, which actually increases over time, but is small. The runoff is very negligible. It's completely negligible. So when we look at the atmosphere versus the ice, at the beginning of the simulations, the ocean gains heat from the atmosphere, but loses heat to the ice due to the ice melt. However, over time, as the sea ice declines, heat loss to the ice decreases and the ocean becomes a net heat source for the atmosphere. So next we look at the sea ice heat budget. As we mentioned before, the goal here is to understand the heat exchanges between the sea ice and the atmosphere and ocean. Question is whether the atmosphere or the ocean plays a more important role in providing heat to warm and melt the sea ice. So it's helpful to look first at the background seasonality of the heat fluxes before analyzing how they change with time. So here we look at watt per meter squared rather than Arctic integrated flux in petawatts, because otherwise changes in these fluxes would be tied to the amount of ice present, and hence the flux changes driven by other factors would be masked. So in summer, the ice gains heat, and in winter, of course, the ice loses heat. And the ocean is the heat source for the ice throughout the year, as the ocean is always warmer than the ice. And this flux is largest in summer, which is when the ice melt occurs. And the atmosphere warms the ice in summer and cools the ice in winter. So the residual between the ice heat content change and some of the other terms is shown here in the magenta. So this represents the ice export as well as any error due to the heat budget being calculated with monthly output. And this shows the ice atmosphere heat flux components. So in summer, the ice gains a large amount of heat from the atmosphere due to strong shortwave radiation. In winter, the outgoing long-wave radiation and the absence of shortwave radiation drives ice cooling and growth. So next, we discuss how these heat fluxes change over time to determine what is driving the sea ice decline. And since we're interested in understanding winter and summer sea ice decline separately, we look at both summer and winter. And the heat fluxes are strongest in about December, January, and June through August. So we choose to focus on these periods rather than September and March when the heat fluxes are pretty weak. So in winter, the surface heat loss increases over time. The ocean to ice heat flux changes very little, and the heat loss to the atmosphere increases over time. And then there's a very small residual term. And this shows the decomposition of the green curve on the left into components. So the increased heat loss to the atmosphere is a result of enhanced sensible and latent heat loss. And the net heat flux into the ice from the, so in summer, the net heat flux into the ice from the ocean atmosphere per unit area increases. And the ocean heat flux also increases dramatically and then becomes very large exponentially as the ice disappears. So in summer, the atmosphere is initially the main source of heat for the ice, although the ocean also contributes. But over time, the ocean becomes the primary heat source before blowing up towards the end of the simulations. And this happens because the fluxes per unit area of ice and the ocean heat fluxes in areas where there's very small sea ice extent, there's very little ice left, still remain fairly large. This is probably due to the ice albedo feedback, where the ocean is becoming very warm and there's still quite a bit of ocean to ice heat flux. However, the increased importance of the ocean still shows up when using petawatts, so it's not simply due to the flux blowing up like this. The residual term is small initially, but then also increases exponentially towards the end of the simulations. So the increase in the heat gain from the atmosphere is driven primarily by a strengthening of the incoming long-wave radiation, which cancels out the outgoing long-wave radiation by the end of the simulations. There are these abrupt changes at around 2015 in the shortwave and net ice heat flux. That is due to the prescribed biomass burning in the model. So in half of the ensemble members, the biomass burning is prescribed according to CMIP6 protocols, and the other half, it's smooth. So in the 50 members that have smooth biomass burning, these curves are much smoother. So here are our conclusions. So the Arctic Ocean warming appears to be driven by increased ocean heat transport through the Bering Straits, as well as the Bering Sea opening. And this is in line with previous studies, which emphasize the importance of the ocean heat transport in driving Arctic warming. And this ocean heat transport increase is largely due to passive temperature changes rather than changes in the volume transport through the sectors. And the sea surface heat loss increases due to enhanced long-wave radiation, as well as latent and sensible heat loss. But this is overwhelmed by the Arctic Ocean heat gain due to enhanced ocean heat transport. And the atmosphere is initially the main heat source for the ice in summer, and the ocean starts to become the main heat source over time. And that's it.
Thanks, Dylan. So are there one or two quick questions? If not,
A quick question for me. If just
great.
a clarifying question, I missed what this is modeled, obviously, that you're analyzing. What are you analyzing here?
Which model? This is the CESN2 large ensemble. So that's 100-member ensemble of different runs, which just have micro and macro perturbations, so small perturbations to their initial ocean and atmospheric states, but otherwise have the exact same historical and future forcing. So the SSP 7.0. So you have at the end of the simulation 7.0 watts per meter squared of additional forcing.
Excellent. Thank you. Very nice presentation, Dylan. Thank you.
Yeah, Martha? Sorry.
Yeah, thank you for the presentation. You pointed out that the volume fluxes through Nares Strait and Fram seem to be correlated. And I was curious if you had any ideas as to why that was happening.
Yes, I didn't have time to show that in the presentation, but we did study that a bit, and this is published. I forgot to add that, but this is published in the Journal of Climate with the same title. But yes, we looked at the wind stress, actually the ocean stress around Greenland. So in the area around Greenland, because you can see that the Nares Strait is on the northwestern part, and the Fram Strait is on the northeastern part. And we saw that there was an increase in kind of in the cyclonic and the cyclonic wind stress, basically, the ocean stress, that seemed to be kind of explaining that.
Thank you.
Thanks, Dylan. So let's move on to Tom. If you have more questions, we can save it for the after talk discussion. Thanks.
Okay, great.
Okay. Sorry. Okay, can you see the screen? Okay, great. Thank you, folks, for coming and listening. So this is a talk about estimating Arctic Ocean salt, heat, and mass fluxes and their budgets. Well, actually, that's a big topic, and so I'm not going to be able to cover all of that, and I'm going to focus on freshwater fluxes and budgets for the Arctic Ocean. And it's going to be a talk that focuses on observational estimates of these quantities, and particularly freshwater fluxes, and observations at gateway sections that Dylan mentioned. So I'm not going to talk a lot about motivation, but I can briefly mention the scientific rationale. So we're interested in freshwater in the Arctic Ocean because it affects circulation in lower latitudes. In particular, it affects the deep water formation and the circulation in the subpolar North Atlantic and the Nordic seas, and therefore affects the overturning circulation in the Atlantic. It's also very important for the stratification in the Arctic Ocean itself. And as you probably already know, that is changing due to climate change with the so-called Atlantification of the Eurasian basin as the beta stratified, the salt stratified ocean disappears in favor of a temperature stratified alpha ocean. And of course, it's relevant to many other things like sea ice and coastal ecosystems and other topics like that. And the other thing that I think, which is a really compelling reason to study freshwater in the Arctic Ocean and how it changes, is that it provides a perspective that allows us to observe the climate dynamics, the change in the system, the mechanisms that are involved in that change, and in particular to anticipate the future changes that, for example, that Dylan was referring to for the heat budget. And I think that that's really quite exciting. And then there's an unprecedented opportunity because we already know quite a lot about the freshwater budget in the Arctic and how we think it works and how we think it might be changing. And we can anticipate future changes, which I think is a really exciting possibility. So let me show you a couple of figures from a review paper by Amy Solomon 3 years ago. And these are time series of the total amount of liquid fresh water stored in the Arctic Ocean from, as you can see, about 7 different reanalysis products. And then the thicker line is the multi-model mean. So what you're looking at here is freshwater content in thousands of cubic kilometers. The freshwater content is defined with this formula. So it is, the salinity is S, and the freshwater content is the volume integrated normalized salinity anomaly with respect to this thing SREF, which is a constant. It's the reference salinity. And it's 35 grams per kilogram in this particular example. You're going to see a couple of other reference salinities, and I'll mention that briefly in passing. But the main point is that as you move from the 1990s through the 2000s, most, perhaps not all, but most of these estimates of this freshwater stored in the Arctic Ocean are increasing by between about 5 and 10,000 cubic kilometers. Okay, and so this particular example is for the region from 70 degrees to the pole. So that includes half of the Nordic seas, and it includes part of Baffin Bay. So it's in detail a little different to what Dylan was showing. In detail, it's a little different to what I'll show you in a moment, but it's more or less the high Arctic Ocean. And then in particular, you can see that there is, in the 20-teens, a stalling of this increase. So you can see that, for example, in the black one, soda. You can kind of see it in the multi-model mean as well, although it's not quite as obvious. The increase in freshwater content in the Arctic over the 90s and 2000s has been known for 15 or 20 years, but this stalling of the freshwater content in the 20-teens is much newer. Now, those are from reanalyses, and we can talk about what goes into the reanalyses of various types. This other squish trace is a time series that is based on in situ observations of Arctic hydrography. So you can go into the Arctic Ocean and you can measure the salinity with CTDs, for example, various other platforms from a SHIP or from an ITP, and then compute this integral with a lot of extrapolation and finger crossing, and then make a time series of that. And I've squished it so it's on the same scale. Here's 95, here's 2015, increased during the 90s and the 2000s, and then more or less a flattening off. And it's increased by about the same amount. It's about 8 or 10,000 cubic kilometers. But there are large uncertainties. There's large discrepancies between the reanalyses, and this in situ Arctic estimate here is an anomaly. So I can slide that up and down the y-axis. It doesn't have an absolute anchor on the y-axis. It's just a change from what it was like in the early 1990s. So how can we independently quantify the liquid freshwater content budget and try and understand the processes that are contributing to these changes? So what I want to talk about is a different perspective. It's independent of what I just showed you, and it's to make observations of the currents and the hydrographic properties at Arctic gateways. And in particular, we're going to be looking at the Bering Strait, Davis Strait, Fram Strait, and the Barents Sea opening. And we could argue about whether or not that's the best choice. It's certainly a common choice, and there are good reasons for doing it. So the Arctic Ocean has the advantage that it's reasonably well constrained by the topography, by the land, so that we don't need to make estimates of ocean fluxes across vast Great Ocean basins. We can do it through a relatively small number of ocean straits. And what you see on the right-hand side, and I'll show you this in more detail in a minute, are these straits compared to each other. Okay, so Davis Strait, about 300 kilometers wide, about 1,100 meters deep or so. Fram Strait is wider, 700 kilometers. About half of it is shelf. Incidentally, this shelf, so that's on the western side, East Greenland shelf. About half of, sorry, most of this shelf is ice covered most of the year. Barents Sea opening is also wide, similar kind of distance to Fram Strait, most of 1,000 kilometers. And the Bering Strait, of course, is very narrow, like 50 or 60 kilometers, and it's only 50 meters deep. Okay, so I'm going to go through these straits in turn and show you the available observations, and then I'm going to try and synthesize them all at the end. Okay, so let's do Davis Strait first. And so this is a slide that was shared with me by Craig Lee. So Craig Lee's from APL-UW, and here are his collaborators. He's currently funded by NSF to deploy moorings at the Davis Strait long-term monitoring section. And here's a diagram showing his typical mooring array. Here's the West Greenland shelf. That's quite wide and shallow. Baffin Island shelf is much narrower. There have been observations in this strait since the 1980s. So the Canadians, led by Charlie Ross, had much reduced array of moorings there from 1987 to 1990. And then Craig started more or less this coverage in the early 2000s and maintained it until 2017. And then there was a gap of about 4 years, and then it was resumed in 2020. And Craig is getting on the ship as we speak to go and turn around the moorings redeploy them, and then they will be picked up in 2 years if he gets funded. So he's waiting for new funding to go and recover and analyze the data. And then most recently, he's also got a bottom pressure gauge here in Central Baffin Bay. So he's got hydrography every year or every other year, some biogeochemistry and biology. And it's now part of what's called a DBO, which is Distributed Biological Observatory. And so there are Canadian and Greenlandic and Danish contributions to that effort. Okay. Now, here are some results from Craig, and these were published by Beth Curry about 12 years ago. So here's volume transport. So this is the net flux across Davis Strait. Davis Strait, incidentally, consists of two-way flow, warm salty Atlantic water flowing in the West Greenland current, and then cold fresh water flowing out in the Arctic outflow. This is the net. So there's a net outflow of about 1.5 Sverdrups. And then this is the freshwater transport. And in this case, it's relative to a reference salinity of 34.8. This is what's published. Actually, what's published ends in 2010, but you can get the data from Craig, I think from the website as well, till 2012. But there are unprocessed, or at least unpublished data from 2012 until 2017. And then from 2020 until, if you wait a month, 2024. So the processing and dissemination of this data is running about 10 or 12 years late, which is awful. It's not because Craig doesn't want to do it. It's just he's not funded for it. He doesn't have the time or the resources. But that's a recurrent theme that I'm going to come back to. There's a lot of data which is just on Craig's hard disk that nobody has access to at the moment. It's coming. Jed Linetsky, who's at Colorado, is working on this, but it's already a decade late. Okay, so now let's move to the Fram Strait, and we split the Fram Strait into two pieces. There's the Western Fram Strait, which carries the East Greenland current, which drains the Central Arctic through the Transpolar Drift. And that is the largest conveyor of freshwater sea ice and carbon and other biogeochemicals out of the Arctic Ocean. And the team at the Norsk Polar Institute in Tromsø have been monitoring this East Greenland current for 3 decades now, since the 1990s, led by Laura de Steur. And I also have information from Paul Dodd on this slide. And so here's the Fram Strait, here's the wide ice-covered East Greenland shelf, and here's the mooring array. And you can see it's in 3 different phases. The early phase just had 2 to 4 moorings in the upper part of the water column. And then they expanded to full depth. And now they've expanded a bit even further in the red box to include some shelf moorings as well. The data are from 1990 to present, more or less without a break, although the array has changed its makeup. They're interested in freshwater and ice being exported, liquid freshwater and solid freshwater. It's split, roughly speaking, 50-50 through the East Greenland current in terms of the net export of freshwater from the Arctic between ice and liquid freshwater. And then they also have quite an interesting comprehensive program looking at biogeochemistry like nutrients, alkalinity, carbon parameters, CDOM, oxygen isotopes, dissolved oxygen, and iodine-129. Iodine-129 comes from the reprocessing plants at Sellafield and La Hague, and it's a useful tracer for pathways and timescales of flow through the Arctic. So let me show you one slide of results from Laura and Paul's work, and this is done by a student, Teo Karpuzoglu, a couple of years ago. And you can see the time series of the freshwater transport here. Now it's referenced to 34.9. This means that it's draining the Arctic. Their sign convention is different to what I showed you a moment ago. And you can see it goes up and down. But they've identified 3 more or less distinct periods, 1, 2, and 3. And then in the lower diagram, Theo accumulated this freshwater transport time series. So this is the cumulative southward freshwater transport that has got units of thousands of kilometers cubed, and then compared it to what's in red, which is the Beaufort jar freshwater content anomaly from Andrei Proshtinsky. So during period 1, the Beaufort jar was accumulating freshwater during the 2000s, like I said, and the outflow through Fram Strait was relatively low, was relatively weak. During period 2, Beaufort jar, I was talking about stabilization for the Arctic as a whole. Well, this data would say the Beaufort jar was diminishing in its freshwater content somewhat, and freshwater transport through Fram Strait was increasing, and then period 3 is a little bit like period 1 again. Increase in Beaufort jar freshwater content, decrease in the outflow through Fram Strait. But if you look at these numbers, so these numbers are here in thousands of cubic kilometers, and compare them to the changes in the Beaufort jar, you find that during periods 1 and 2, so this is accumulation periods in the Beaufort jar, then the diminished outflow through Fram Strait is only about a quarter or a third of the increase in the Beaufort jar. And so there has to be some other process that is causing the Beaufort jar to expand. So there has to be internal redistribution or changes in other fluxes. It's not due to the outflow through Fram Strait slowing down. But during period 2, so this is during the release period, or the stall period of the Beaufort jar, then the increase in the outflow through Fram Strait accounts for about 2/3 of the change in the Beaufort jar. So the idea is then that most of the, maybe 2/3, it's plausible to think that 2/3 of the freshwater loss from the Beaufort jar is actually drained through Fram Strait. Okay, so now let's look to the east in Fram Strait. This is called the West Spitsbergen Current Array. It's maintained by Arvi and Wilken John von Alpen and Rebecca McPherson, the people who helped me with this slide. The West Spitsbergen Current transports the warmest water into the Arctic, more than 3 degrees C, Atlantic water. It's very salty. So this is analogous to Davis Strait, right? Inflow of warm, salty water on the east, outflow of cold, fresh water on the west. It's very difficult to measure this because the strait is relatively wide and the currents are relatively narrow. So you can see here the vectors showing the West Spitsbergen current core. Then they have this region here, which is the offshore branch, and then there's a recirculation in Fram Strait. So RV currently has 5 moorings at 79 North, and there's an institutional commitment to maintain that array. They go all the way to the bottom. Sometimes they have high resolution for stratification and biogeochemistry, but they move the moorings around. So they were 50 kilometers further south until 2016, and then they moved further north. And that's because the recirculation in the eddy field in the central Fram Strait is a real challenge. It's difficult to have, at reasonable cost, a comprehensive coverage of this strait. Now, I can tell you, based on a presentation that Rebecca gave in May at an ASOF meeting, that the West Spitsbergen current transport has been decreasing in the last 20 years in the offshore branch, not in the core, but about a factor of 50% diminishing of the transport, volume transport in the West Spitsbergen current offshore branch. The core of the current, its transport hasn't changed, but it is warming, and presumably it's also getting saltier. So Rebecca is writing this up, and watch out for a paper on that soon. It's going to go to deep sea research. Okay, so now let's move to the Bering Strait. So it's narrow and it's shallow, but there are complications here, of course, because half of it is in Russian territorial waters. In the early days, there was access to that part of the Bering Strait, and now there isn't. So the moorings, which are operated by Rebecca Woodgate from University of Washington APL, are here on the eastern side in the US waters. And then this A3 mooring tries to capture everything. They've been running since the 1990s. Since 2006, they've covered the Alaskan coastal current. Sorry, that's in 2001. And then more recently, they've included this A3 mooring as well. Just move that. And they have annual hydrography too. Okay. So let me show you a couple of results from Rebecca. This is probably the best record that we have of any of these 4 straits because it's sufficiently narrow that there's only unidirectional transport. There's not two-way flow. Transport has been increasing. The nominal number is a Sverdrup, and it's been increasing over the last 20 years. The temperature has been going up and down. We thought it was warming for a while, but then there was quite a long period when it got cool and returned to sort of previous temperatures, similar with the salinity. And then Rebecca computes the heat and the freshwater transports as well, which will go into the synthesis I'm going to show you in a moment. So there's a significant volume transport increase over the last 20 years and no significant change in any of these other time series. Okay, Barents Sea opening. So the Institute for Marine Research in Bergen operates the monitoring program here, and Randy Ingveldsson sent this information. So there's a warm, salty Atlantic inflow into the Barents Sea and then subsequently to the high Arctic. It's wide. It's never really been adequately monitored. IMR operates 5 moorings. Most of the time, they've only had temperature and point velocity measurements. More recently, they have ADCPs and also salinity. But they do have roughly 6 hydrographic sections per year between northwest Norway and Bear Island, which is here where the section ends. And here is a time series of volume transport from Randy. So there's no long-term trend in volume transport. Variability is quite large, and you can find periods of, say, about a decade where there's a significant trend, like here, it's dropped by 70% in the last 10 years, roughly speaking. Okay, so how do we put all of this information together? Well, I think the state of the art of this is work by Taka Chibuchi and Sheldon Bacon and collaborators, and they had a nice sequence of papers. The most recent one was in the spring of this year, and I'm showing you results from that. And so what they do is they take the hydrographic observations, they take the moorings, they do a geostrophic inverse calculation to figure out the level of no motion, and then they conserve things that they believe should be conserved, like the total amount of mass, and then they can also figure out the total amount of heat and freshwater exchange. So I'm going to show you the liquid freshwater results. So here's the solution for the velocity field. So for instance, this is the West Spitsbergen current flowing into the Arctic. Here's the East Grin current flowing out. This is the salinity field. So it's salty going in, it's fresh coming out. And then these curves show the stream function for the liquid freshwater flux into the Arctic as a whole. So it starts over here at 0 on Baffin Island, and then you go all the way around to Bering Strait. Now, Taka has computed this with respect to 3 different reference salinities. So I've showed you 34.8 most of the time. And you can see that the individual curves depend on the reference salinity. And that's because there's an ambiguity in interpreting a flux across a strait where there is a non-zero volume transport. If you use liquid freshwater content computed with respect to a reference salinity. So for example, you would come to different conclusions about the role of the East Greenland current depending on your reference salinity. Now, the choice of reference salinity is arbitrary, so it means there's no physical significance to interpreting this flux in isolation. But notice that because the Arctic mass is conserved overall, they all end up coming back to the same point over here on the right-hand side, which is about 100 millisverdrups. Okay, so I'm going to convert that into cubic kilometers per year in a moment. So this is the flux of freshwater carried by the seawater, by liquid seawater, and we need to add sea ice to that as well, which TACA does. It's just not shown here. Okay, so this is the average for the period 2005 to 2010, which is this highlighted region on this time series where you can see where the data are available. And let's try and make sense of this number and compare it to the reanalyses I showed you at the start, and then I'm going to wrap up. So that 100 millispheredrops number, that's the average over this 5 or 6 year period. Here's a diagram showing a time series. So that's this red dashed line. Okay, so the average of this red dashed line is 100. You can see it has a seasonal cycle. Here's a low pass filtered time series, and you can see it's declining. And here's the component due to the sea ice. So it's about 100 millispheredrops due to the liquid and about 50 due to the sea ice, which gives you a total of about 150 millispheredrops. Sea ice doesn't have much trend over this period, so the total has a declining trend. Okay, and that doesn't mean that the Arctic sea ice export hasn't changed. So remember that this is just 2005 to 2010. It's already quite out of date. And so, for example, in Fram Strait, there's been large regime shifts seen in sea ice exports, but they would be happening in the 2010s and in the 2020s. So this decreasing freshwater export flux overall has implications for the storage of liquid freshwater in the Arctic. So let's try and see how that works. So here's the two diagrams I showed you at the start. And here is the change that you would expect in the freshwater content of the Arctic as a whole due to the decline in the export of fresh water across the gateway sections from the Arctic into the lower latitude ocean. So you can see that the increase is at about 4,000 or 5,000 cubic kilometers over about 5 years, and it fits reasonably well with these other increases. Okay, the period of observation is during the period of increase of liquid freshwater, and then you have the hiatus period in the 2010s. So this assumes, if you're going to believe this assumes that the other sources of fresh water to the Arctic haven't changed. And so they're precipitation minus evaporation and then runoff. And those are not small. It's plausible that the real system changed because the oceanic convective fluxes changed. But it's also quite reasonable to think that P minus C plus R has also changed, and that needs further investigation. Okay, this is my last slide. So the challenges involved in making these measurements, they're to do with the fact that the deformation radius is really small, like less than 10 kilometers. So Fram Strait, Davis Strait, and the Barents Sea opening are dynamically wide. It's really hard with that deformation radius to have a comprehensive mooring array because you just need so many moorings. The ice and the remoteness of the location, of course, is a problem. Modern instruments need to communicate with satellites. They can't do that because of the presence of the ice. Most of the fresh water is carried right at the surface. If you put instruments right at the surface, they can get destroyed by sea ice. Instruments on the shelves can get scoured by bergs, and a lot of the really important currents are on the shelves, like the East Greenland current, for example, and it's just expensive and inaccessible to get up there. But there are several opportunities, and I think that overall this approach is really important and promising. It's essential that we extend this gateway inverse model to the present. So it ends in 2010, but we have data till 2022 right now. That is underway, but it's taking some time. So there's a project in Europe called EPOC, which stands for Explaining and Predicting the Ocean Conveyor, and Hege Birte Fredriksson is doing this extension of the inverse model to present. So I'm hopeful that within a year or two, we will have a time series that runs all the way through the 2010s. And then we need to operationalize that inversion, synthesis, and dissemination process so that we don't, as a community, have to wait for 10 or 12 years and a particular project getting funded in order to get this update. It needs to be done, turned around on a timescale of months or so, I think. We need to combine those estimates with meteorological estimates of P minus E plus R, so we can infer liquid freshwater volume change in the Arctic control volume as a whole. We obviously need to maintain the observing network, which is very difficult. Only one of those 4 gateways has secure funding beyond 2026. And we also need to expand the network to include biogeochemistry, because you can do the same kind of thing with nutrients and carbon and so on. Okay, finally, 2 adverts. If you like this kind of thing, Isabella Labra has a nice paper under revision for JGR, and she's giving a seminar at University of Maryland College Park next week on budgets and fluxes. And then ASOF, which is the Arctic Subarctic Ocean Flux Program, does all of this stuff, now led by Rebecca, Laura, and Vilken. And the next ASOF meeting, to which you're all invited, is in May in Barcelona. Thank you.
Thanks, Tom, for a very nice talk. So any questions? Great. Yeah, we still have a few minutes, and both to Tom and to Dylan. Any burning questions you have? I guess I have one. This is both to Tom and Dylan. The Bering Strait. I mean the Pacific sector, near the Pacific sector. So I kind of wonder, the volume transport. I think Dylan, in your long-term projections, it shows it to decrease in the future. And I'm just wondering, to the first order, what is control that volume transport decrease? You know, the CI system. I mean, itself is a lot controlled by the sea level height difference between the Pacific and Arctic, right? So how do those processes change with climate change?
Oh, I'm actually not sure. I think maybe Tom has a better answer for that, but I'm not sure. I didn't really investigate what caused the change in the volume transport.
That's fair. Wilbert, you have your hand raised.
Yeah, very nice talk, Tom. We had the conversation earlier this week at US Cliver as well. This was great to see both of your presentations. I guess with these observational networks, it seemed kind of ad hoc, right? And is there any international coordination about maintaining these observational systems, maybe moving them from research-based funding agencies to operational agencies? And what role could maybe IARPIC or US Cliver or even International Cliver play in that? And Milena is part of the panel of the Northern Oceans for International Cliver. So do you have any thoughts on that? How these networks can help?
It's always, I would say it's almost always been grassroots. So it's individual scientists like the people I mentioned, writing individual proposals to their national research agencies, you know, and they make the case, they get the funding, and they do it for a few years. And then it's grassroots in the sense that those people then come together, like at ASOF meetings, and put their data together, and then hopefully there is a net benefit for everybody because there's a synthesis which puts it all into context. I don't know if there's ever been any serious attempt to make it operational, to move it out of research agencies. I guess that's partly occurred in Europe at RV. So the Norwegian institutes, the BSO, for example, is a fisheries mooring array, I believe, and there's every 2 month cruises are fisheries cruises. But I think that it would definitely benefit from coordination from groups like Cliver, and emphasizing that this is a sort of important diagnostic product of the state of the Arctic climate, and it's worth maintaining. So, I mean, Davis Strait was unfunded for 3 years, and Craig tried extremely hard to get it funded. He got consistently superb science reviews, and it's just expensive, and the agency didn't have enough money. Eventually they did. So it's fragile. but important.
Right. So then to follow up on that, I mean, there is international collaboration on Argo, the Argo network, and people are working hard on developing the technology to make these floats usable in the Arctic as well. Would that system be able to replace these monitoring systems if they were able to stay under the sea ice, if they didn't have to deal with those challenges?
So I can't answer the specific question about could they be replaced. My intuition would be no, they couldn't. It would be a mistake to just rely on Argo style measurements in the basins and remove all the moorings. So as we mentioned a couple of days ago, that there are efforts to develop under ice Argo and also under ice sea gliders. Craig has part of the Arctic insonified right now. You need sound sources for navigation. But actually, even if you don't have any sound sources there, it's useful data. So without a sound source, you don't know where the profiles are from. But so there's an error in the location of the profiles. But nevertheless, it's still valuable information. And it's not, I don't think it's a huge effort to insonify the whole Arctic, as I spoke to you about on Tuesday. The technology for the Argo, sort of the ice-aware Argo float and sea gliders is pretty mature, so they can swim around under the ice. They figure out when the ice is there and when it's safe to surface and so on. The final thing to say is the point about a lot of the boundary currents carrying a lot of the fluxes being in shallow water and on the shelves is really important, because you can't operate Argo and sea gliders on the shelves. So for the shelves, you're always going to have moorings, I think.
Great, thanks for your feedback, Tom.
Okay, so thanks very much to both our speakers, and then and thank you everybody for participating. So I think we will see you in about another month, right? There will be the next installment of our discussions. So thanks again, everyone. We'll see you later. Thanks, Tani.
Yeah,
Thanks,
thank you.
everybody. Thank you,
Thanks,
Tom.
everybody.
Thank you, Dylan.
Bye-bye.
Bye.